Pendulums are another of the two oscillations that we talk about that are very similar to everything else and still apply to everything else, but are in their group of their own. Pendulums are attached to a pivot point, and much like circular motion, it does move in a circular pathway. So because of that, it does obey the rules of circular motion. Now, when we talked about springs, we had our total potential energy, and we had our total kinetic energy, and that's the same for our pendulum. So at the very top, we have total potential energy, and at the very bottom, we have total kinetic energy, much like our roller coaster. The total potential energy is going to be the same as what we found before, which is mass times gravity times height, and the total kinetic energy is still going to be 1/2 mass times velocity squared. We do have our centripetal force, or our tension that's keeping it in, and at different varying positions along the way, we can determine what that tension is. We always have the length of the pendulum, which is equal to the length of the string. And so this length of the pendulum is actually what determines how long that pendulum takes to move from one to the other. It's not dependent upon the mass of the object on the end of the string. It's not dependent on the gravity. It's dependent on the length of the string. This is what you can see when you're talking about like grandfather clocks or cuckoo clocks. The more the length is of the bobber, the faster or the slower it'll go. The higher up the bobber is, the faster it'll go. And you can see this in old-timey wind-up cuckoo clocks where you can actually set the pace of the timekeeper by changing the height of the bobber. So here we have total potential energy, and here we have total kinetic energy. And at this point, we don't have total of either, but we have potential plus kinetic energy to find our total energy. We can determine what that potential energy is by seeing the difference between the lengths at the very base and at the height from where it is. You're still going to have the same length here as you do here. Those don't change, but the height from the base is what's going to change, and so you can determine that from this aspect. So you have the total length, and then once you find the height of the vertical, you subtract that from the total length, and that's the height here. The last part about pendulums that we need to understand is the period of the pendulum. So since we were talking about circular motion, because it does obey the rules of the circular motion with the centripetal force pulling in and the tension, then we have to have the period. So the period of the pendulum is how long it takes to complete one complete rotation. So it starts at one point and ends back in the same point, much like the springs. So the period of a pendulum is equal to 2 pi. Here's that circular aspect again. Times the square root of the length of the string, because that is actually what determines how long the period is, divided by gravitational force, because that is, or gravitational constant, the gravitational acceleration, because that's what's causing the object to move back and forth. So period of the pendulum, 2 pi times the square root of the length of the string divided by the gravitational constant of acceleration.